So in the previous chapter we looked at the gas power system. Now we are going to look at refrigeration and heat pump system. So in this case our goal would be to look at the basic vapor compression cycle for refrigeration system. We are going to look at basic thermodynamic model, PV and TS diagram and property evaluation, then look at the energy balance and entropy balance, and then coefficient of performance. So very similar analysis that we did for gas power system, and you recall from earlier chapter 5 or chapter 2 that refrigeration or heat pump cycle is basically reverse of a power cycle. So it has the same components, but it works in the opposite direction. So a Carnot refrigeration cycle is exactly opposite or reverse of a Carnot heat cycle. So again, it has the same four components. You have a turbine, compressor, and the two heat exchangers basically. So in this case, let's say start from here where you have the working fluid going to compressor. So it gets compressed, that means you are doing the work on that. Then it goes into the condenser where the heat is rejected, so it's thrown out of the system. Then it's pushed back into the turbine, and then where it expands basically and does some useful work, and then it's put back into the evaporator. So in this case, let's say if you look at your regular refrigerator in your household, the evaporator is basically inside of the refrigerator chamber where you keep your food. The compressor is the one where you hear the sound whenever it's running. The condenser then throws the heat which has been taken out from this evaporator into the outside atmosphere. So the warm region TH would be basically the room temperature, and the TC here would be the temperature inside the refrigerator. And then you have a turbine, which normally in a refrigerator system that you have at home, we don't really have a turbine. So this would be the ideal situation, and then we will see a little bit later how we can replace this turbine by something which is much more inexpensive, because in a refrigerator at home we don't really care about generating any power. So if you need to represent this cycle on a TS diagram, then we have two processes, two equipment, turbine and compressor, which are isentropic, and then we have condenser and evaporator, which are isothermal. So 1 to 2, which is compressor, is isentropic. So that basically takes something which is maybe two-phase mixture and brings it to the saturated vapor. Then 2 to 3, which is the condenser, where the heat is being rejected. So that goes from saturated vapor to saturated liquid. Then turbine expands it, so that becomes a two-phase region. And then from 4 to 1, heat is being picked up in the refrigeration cycle from the refrigerator, or that's the evaporation cycle. So Q dot in is the rate at which the heat is being taken in, and the Q dot out is the rate at which the heat is being rejected to the outside atmosphere. And so this would be the TS diagram, which is very simple, straightforward TS diagram. So let's look at each of these steps. And of course these are all of them, for our purpose we are going to assume they are internally reversible processes, so we are not worried about irreversibilities at this point. So if you look at these processes, 4 to 1, which is the process going from here to there, here, or the time when the energy gets picked up from inside the refrigerator, that's a constant temperature evaporation of two-phase refrigerant mixture where heat is being added to the working fluid. Then 1 to 2, which is the compressor cycle, so adiabatic compression of refrigerant mixture to saturated vapor state. 2 to 3 is the constant temperature condensation to saturated liquid state where the heat is being rejected. And then 3 to 4 with adiabatic expansion through the turbine. That's this one right there. 3 to 4 goes right there. So that's the complete cycle. So the coefficient of performance, which is Q N dot or M dot divided by amount of work that's being done. So remember, you are doing certain amount of work here, but then you are also taking some work out from the turbine. So this is the net work done during one cycle. And so if you look at this, this can be basically looked at on a TS diagram as the area under a certain curve. So Q in, which is the process 4 to 1, so that's this process 4 1. So Q in would be just the area under this curve, which will be area of 1AB41, which is 1AB41, that lower rectangle here. And the amount of work, net work done would be nothing but the difference in the heat transfer, or these two energies. So that will be the area of this rectangle, area of the rectangle 1 2 3 4, and so that's what this area is, 1 2 3 4 1. And so now, since we know how to calculate this area under the curve, because they are just straight lines, we can replace this areas in terms of the temperature and the change in entropy. And so that means the beta max, which is the coefficient of performance, is Tc over Th minus Tc. So the formula itself is nothing new, but it can easily be derived from the area under the curve of this TS diagram. Now, as I said earlier, that normally, especially when you're talking about the refrigeration at your home, the refrigerator at your home, you don't really have a turbine there, because there's not really much value in producing power there, and turbine usually cost quite a lot. So instead of that, we want to replace it by some very simple, inexpensive device. So the turbine is basically replaced by a throttling valve or an expansion valve, which basically expands the gas. And then normally in the compressor, instead of pumping in a two-phase mixture, is what you do is basically bring it all the way to at least saturated vapor state, so that always a single phase, it's much easier to pump or compress a single phase mixture than a two-phase mixture. So instead of stopping at one here, you go all the way up to the end at least. So that's what this is. The one becomes saturated vapor. Then of course it's an isentropic process, still an isentropic process here. So it goes straight up. That means you get a superheated vapor here. And then it's going to be cooled. That's where this heat is released and gets to 0.3, which is at the end of this heat exchanger, where you are throwing the heat away into the outside atmosphere. And then it gets, instead of a turbine, which is an isentropic process, now you have an expansion valve. And basically for the expansion valve, the enthalpy remains constant. So enthalpy at 3 is same as enthalpy at 4, but it's not an isentropic process anymore, and that's why it doesn't go straight down. So this expansion process or expansion valve is shown here by this 3 4. So now if you look at the 4 steps here, 4 processes here, again they are internally reversible, we are assuming. So we have 1 to 2s, which is an isentropic compression of a refrigerant. Then 2s to 3 is a constant pressure condensation, which is this one right there, where the heat is being rejected to the outside atmosphere. 3 to 4 is the throttling valve that takes saturated liquid to a two-phase state. So that's where this one is, 3 to 4. And then 4 to 1 is a constant pressure evaporation. So this is your still inside the evaporation chamber of the, or inside the refrigerator basically, which is your evaporation chamber. So now if we take into account the fact that we have an expansion valve rather than a turbine, then we can again calculate coefficient of performance here. So isentropic process, Q12 would be equal to 0, and if we assume a closed system, that means the same gas is being circulated. It could be air, it could be freon, anything else. Then the work done during the compression, or the energy work that is done on the system during compression, would be given by H2 minus H1. The heat taken out would be H2 minus H3, and the heat that is put in is H1 minus H4, and this Q in dot, that is the amount of energy that is being, the rate at which it's being taken out, that's called refrigeration capacity, which is normally given either in kilowatts or BTU per hour, or also in tons, which gives you in terms of ton of refrigeration. And using this the fact that H3 equal to H4, so during the throttling process the enthalpy doesn't change. Now if you replace this Q's and W's by the corresponding change in enthalpies, we get a coefficient of performance, which is given by H1 minus H4 divided by H2 minus H1. So this would be the coefficient of performance in terms of when we have a expansion wall in place of a turbine.